Now we address the question of whether you can form some combination of V1, V2, and V3, some sum of multiples of these three vectors to get any vector in the plane, or in space, in R3. Okay, well, a general vector in R3 is represented by a column vector with three arbitrary symbols. Somebody suggested using A, B, and C. Okay, that's fine. Okay, we got A, B, and C. Now, V1 is the vector 3, 2, 4. V2 is the vector negative 2, 1, 5. And W3 is the vector 2, 3, 4. So this equation translates into this form, multiplying through by my C1, C2, and C3, and I haven't included all the steps. They're just the same as they were in previous examples. We get ultimately the matrix equation 3, 2, 4, negative 2, 1, 5, 2, 3, 4 times C1, C2, C3, which incidentally is the same matrix equation, the same left-hand side we had before. But now, instead of being equal to 0, 0, 0, it's equal to the column vector ABC. Okay, well, that means that C1, C2, C3 is the inverse of this matrix multiplied by ABC, provided only that the determinant of this matrix is not 0. Things have gotten a little smudged moving this board around. Try to make it look a little worse. Okay. Provided this determinant isn't 0, which do be so. Okay. And you can again check that, but it's the same determinant. I said you could check before. So it wasn't 0 then, it's not 0 now. It still isn't 0. Okay, so we can invert this matrix and multiply it by A, B, C and get our C1, C2, C3, and we don't expect to get 0, 0, 0 because these numbers aren't all zeros. And since this vector is invertible, if they aren't all zeros, you're not going to get all zeros here. Okay, that's one way to answer this question. You can invert this matrix, so no matter what A, B, and C are, you're going to get C1, C2, C3 that allow this combination of the three vectors to add up to A, B, C. Alternatively, we take this equation and we write out the system of matrices, the system of equations that we get out of this, and we get an augmented matrix, which just contains this matrix whose determinant is not 0, and then our A, B, C. Okay? Now that reduces to the identity matrix in three numbers over here. So C1 is this number, C2 is this number, C3 is this number. Again, provided that this matrix can be reduced to the identity using our standard row operations. Do we know that this matrix reduces to the identity? How do we know that this matrix is going to reduce to the identity? Well, a lot of ways to think about this. We know the matrix is invertible because its determinant isn't 0. So if we augment this matrix with the identity, we have to be able to reduce it in order to get the inverse. Since the inverse exists, it's going to be possible. Many other ways to make that connection, but the point is this reduces to this, provided this reduces to the identity, which it does because its determinant isn't 0. Okay, now those are all properties you got to be aware of so that this all makes good sense. And of course you need to have practiced this and written out the equations of this form, put them into this form, continue simplifying, express them as systems of equations, express them as matrix equations, and think about what it all means.